All right, today we're going to follow the entire secret life of a battery, from the raw materials that give it life all the way to the huge challenges of its afterlife. Let's dive in.
You know, batteries are kind of the invisible engine of our modern lives. They're in your phone, probably on your wrist, and they're the power source for the electric cars that are completely transforming our cities. They are, quite simply, everywhere. We charge them, we use them, and then, well, we replace them. But have you ever stopped to think about what happens before they even get to us? And maybe more importantly, what happens after? What's the real story packed inside that little metal case? So we're going to peel back the layers on this essential technology because its story is about so much more than just chemistry. It's a story about massive industrial innovation and, frankly, a huge environmental challenge that we absolutely have to solve.
Okay, so let's start at the beginning. This never-ending quest for a better battery. For decades, the goal seemed pretty simple, right? Just find new materials to make them better. But as it turns out, it's not nearly that straightforward.
And you can see this progress in the very phone you might be holding right now. I mean, the first iPhone battery had a capacity of 1,400 milliamp hours. Just a decade later, that nearly doubled. And today's models pack in over 4,000. That incredible leap is a direct result of breakthroughs in material science.
But here's the catch. For every single material that makes it, countless others fail to make that leap from the lab to your device. And that's what scientists call the valley of death. This, perilous gap between a brilliant discovery in a lab and a product you can actually go out and buy.
You know, this kind of challenge, it's not new at all. In the late 1800s, people seriously thought major cities would be literally buried under horse manure. It seemed like an unsolvable crisis. And then, the internal combustion engine came along and just made the entire problem obsolete. It's a great reminder that breakthrough solutions often come from the places you least expect.
So, a great idea in a lab is one thing. But how do you take that idea and turn it into millions of batteries for millions of cars? Well, that is a whole different ballgame. It's a completely different universe of challenges.
See, it all comes down to scale. A researcher might cook up something totally revolutionary. But we're talking about a few milligrams of powder, like a pinch of dust. To power the EV revolution, we need over 2 million tons of these materials. That jump from a milligram to a megaton, it is one of the biggest hurdles in the entire industry.
And get this, it's not a simple one-and-done process, not even close. To make just one part, the cathode, you have to dissolve metal salts, precipitate them, dry them, mix them with lithium, bake them at over 800 degrees Celsius, and then wash and coat them. Every single one of those steps has to be perfect, every single time, on a massive industrial scale.
So, because that whole process is so incredibly complex and expensive, scientists are of course looking for other options. Lithium-ion batteries depend on materials like cobalt, and their prices can go wild. But new technologies like sodium-ion batteries, they use stuff that's way more abundant and cheaper. We're talking table salt and aluminum. This could be a total game changer for more stable and sustainable energy storage.
All right, so we've made the battery, it's powered our car for a decade, now what? Well, now we enter what might be the most critical and definitely the most challenging part of its life, the afterlife.
And right here, we need to get a really important distinction straight. Recovery just means you got the materials back, but recycling, that's the real prize. A material is only truly recycled if it's pure enough to be sold and then used in a brand new product. And believe me, that second step, it's way, way harder.
So, what makes or breaks whether something actually gets recycled? Well, it really boils down to some pretty basic economics and physics. Is the material valuable? Is there a lot of it to begin with? Can you purify it easily? And this is a big one. Does it still work after you recycle it? If the answer to any of those is no, it probably just ends up in a landfill.
Which of course brings us to the million-dollar question. We are facing a tidal wave of used batteries, and in response, governments are finally stepping in with some pretty strict new rules. So, can the industry actually hit these ambitious targets? Just to give you a sense of the scale we're talking about, listen to this. By 2035, the UK alone is expected to generate 150,000 tons of EV battery waste every single year. That's enough to fill dozens of Olympic swimming pools. And remember, that's just one country.
And here is the absolute heart of the economic problem. Almost all of the financial value in a battery, we're talking up to 95%, is concentrated in just 4 metals: cobalt, nickel, lithium, and copper. What that means is there's almost zero financial incentive to recycle anything else, like the graphite or the plastic. So, since the market won't solve this on its own, regulators are stepping in and forcing the issue. The European Union, for example, is rolling out some really aggressive new mandates. By 2025, recyclers have to hit 65% overall efficiency. By 2030, that jumps to 70%, and they've got specific targets for each individual metal. These rules are basically designed to force a truly circular economy for batteries into existence.
Okay, so as we start to wrap this up, it's pretty clear that while we've made some incredible progress, there are still some massive challenges ahead. So what are the key hurdles we still have to clear for a truly sustainable battery future?
I absolutely love this question, which was actually put to a panel of battery experts. If you could wave a magic wand and fix just one thing in the entire battery ecosystem, what would it be? You know, their answers really get right to the heart of the matter.
And here's a perfect example of just how tricky this all is. Newer battery chemistries like LFP, that's lithium iron phosphate, they're fantastic because they don't use expensive cobalt. But here's the paradox. That very lack of valuable metal makes them much harder to recycle economically than the older NMC or nickel manganese cobalt batteries. Sometimes, solving one problem just creates a whole new one.
So you can see how all of these challenges are completely interconnected. We have to solve that massive engineering problem of scale. We have to start designing batteries for recycling from day one. And we absolutely have to create a real thriving market for all the recycled components, not just a handful of valuable metals.
And all of this really brings us to one final and I think crucial point. That classic image we have of a lone scientist having a eureka moment. It's a great story, but it's not how we're going to solve this.
See, progress here isn't about one person in a lab. It needs a whole village, a whole ecosystem of chemists, engineers, manufacturers, policymakers, all working together. The real breakthrough isn't going to be a single new material. It's going to be the global system we build to create, use, and reuse these incredible devices sustainably. Thanks for watching.